30 years back only we are creating the 3D objects by virtual mode only. Later they are into the additive manufacturing process computer in the field. We are getting the prototype by using of 3D model into the 3D components. So it is the form of additive manufacturing. It is a process of joining the material to make an object from the 3D model data by layer process, that is a slicing or adding of the materials. It is a process of joining materials to make the object from 3D model data, usually layer upon layer, as opposed to the subtractive manufacturing materials. So this is the basic common procedure for how to making the three-dimensional diagram into the three-dimensional real type objects. Initially, we are creating the object by using of any one of the modeling software, maybe AutoCAD or Pro E or KD or Unigraphics, whatever maybe. After completing the process, we are converting the 3D diagram data into the STL file formats. Later, the file format should be transferred to the machine setup based on the input of recurring machine input. Later, it should be formed by using of any one of the additive manufacturing technology method. Later, we are removed from the job from the additive manufacturing machine. We are going for the post-process techniques for getting the final accuracy and precision dimension of the object. Finally, it go for the applications. So this is the additive manufacturing applications timeline started from the 1988 to 2032. So from the 1988 to 1994, generally we are using the rapid prototyping. Then we are advanced with the rapid casting process. In the year of 1995, it is come for the rapid tooling, and 2001 onwards they are using for additive manufacturing for automotive applications, that is the interior and exterior lightweight applications. From 2004 onwards, they are using the polymer-based additive materials for aerospace application. From 2005, they are using the polymer for medical applications, that is the implant of some artificial bones and artificial screws and nuts. And 2011, they are using for the aerospace application. Previously, they are using only for polymer materials. Later, they are introducing the metal-based additive manufacturing for aerospace application. And 2013 to 16, they are using nano manufacturing parts by using of additive manufacturing. Up to 17 for architectural design. From up to 18 biomedical implants, and up to 22 they are using in situ biomanufacturing. They are using the materials and bio-based product for making the better suitability. So 2002 to 32 they are fully focusing for the full body organs. So these are the some typical applications for additive manufacturing in the various mechanical sectors. For aerospace, they are making some component for tool and mold making. For electronics, they are preparing the electronic chips and sports equipment and toys and collectibles and prosthetics and orthotics for the handicapped patients, and for textile manufacturing, for furniture, for surgical device and implants, jewelry and automotive. Nowadays, additive manufacturing used for the all the engineering sectors. And in some of the advantages and disadvantages also having the additive manufacturing, it's for some advantages of freedom to design and innovating without any penalties, because we are making the component with low cost and the rapid iteration through the design permutation. So there are a number of trials and a number of trials we can go for the manufacturing, excellent for the mass to customization, elimination of tooling, green manufacturing, minimal material waste, energy efficient, and enable personalized manufacturing. Some of the concerns are unexpected pre and post processing requirement, because of, suppose we are going for selecting the some alternative material or some of the specialized material, the cost should be very more. For best example, for fusion deposition molding, up to 200 temperature, up to 200 degrees centigrade, the material machine cost is very less. Suppose we are crossing the more than 300 degree centigrade temperature, the cost of the equipment is completely high, and it is a high process cost, lack of industry standards, low speed and not low speed are not suitable for the mass production, inconsistent materials, and a limited number of materials, and high equipment cost for high-end manufacturing. So generally, additive manufacturing should be classified broadly in three categories. One is the formation methodology of formation of the product based on the types of base material used and medium of use for the processing. Based on the formation of the product, material jetting, photo polymerization, material extrusion, and sheet lamination, binder jetting, powder bed fusion methodology, and energy deposition. Types of materials used, solid based material usage, powder based material using, and liquid based material using. And medium used for processing laser beam or ultraviolet rays or thermal rays. So based on the material extrusion, generally we are using the polymer materials or sand-based material. The most common technologies we are using is fusion deposition modeling, and sheet-based is polymer and metals. Also, both the metals are used. Generally, we are using the LOM methodology or ultrasonic consolidation. For powder bed fusion process, generally we are using the polymer materials or metals and ceramics and sand and carbon materials. So related technologies are electron beam melting, selective laser sintering, and selective heat sintering and direct metal latter sintering. For material jetting, polymers, metals, wax, and biometals also we are using for the material jetting process. The major technologies we are using for the material jet is multi-jet modeling methodology. For binder jetting, we are using the polymers, metals, and glasses also. For technologies, powder bed and inkjet head, and plastic-based 3D printing. For DED process, powders and metals are widely used. Laser-based metal deposition method process are generally used for dead process. For photopolymerization, polymers and ceramics and wax metals are used. For technologies are stereolithography and digital light processing technology. The first one is the material extrusion process. This is the most common technology widely used for the entire world. This desktop models are nowadays the desktop models are widely used for preparing the student projects also. It is inexpensive at the home 3D printers. The material drawn through the materials drawn through the nozzle and heated in the depths of the continuous stream. The nozzle moves horizontally and platform moves up and down vertically. Because of the materials are heated, material when it is applied, it fuses the previous layer by layer. The bonding between the layers can also controlled through the temperature and chemical agents. So commonly, we are using the polymer and the composite based filaments. The extrusions are moving on the three axes X and Y. The parameters and optimization can be used by artificial intelligence. So, what are the challenges generally we are facing in the fusion deposition model is warping process. It's a dimensional decrease during the solidification because of maintaining of building platform temperature is different and the nozzle temperature is different. Due to the deposition of the metal, at the time we are facing the challenge of warping defects and layer adhesion. Layer to remelt and enable to respond is the previous layer. The temperature difference is making the two defects in the fusion deposition modeling and support structure and infill shell patterns. Because for, suppose we are going for the fusion deposition modeling, we are having a different input parameters, so layer thickness, layer infill density, kerf angle, and different patterns. So some of the patterns is not affecting any one of the built platforms. Suppose we are changing the pattern methodology, definitely it's required some support structures. After post processing, we are removing of support structures, the very costly process. The main characteristics of fusion FDM 3D printers are thermoplastic materials generally using, that is PLA, ABS, PET, GP, CPA, and PEEK, and some other materials. And dimensional accuracy plus or minus 0.5 percentage. And typical build specs are maximum 200 into 200 for desktop. For industrial purpose, 900 600 into 900 for industrial purpose. Common layer thickness is 500 to 400 microns. It supports sometimes depends upon the depends upon the layer structure only. It's required the supports, otherwise it's not required the support structures. And next one is the material jetting. The print head is above the platform. Material is deposited on the surface in the form of droplets. The hundreds of the micro droplets are positioned with the charge deflection plates, providing the increased control and accuracy. These droplets are solidified and repeated build up the layers. The basic common process for all the additive manufacturing is what object is basically we require. You can just create in the 3D modeling. After the file should be converted in the machine accepted file format. Generally, they are converted to the STL formats. Layer, the file format should be transferred to the FDM printing machine or binder jetting or SLM or DLM, whatever machine the additive manufacturing technologies are using. Later, it should be only the working process should be different. That is maybe a material extrusion, or it's preparing the sheet lamination, or you are spread the powder, you are passing the electron beam or laser or material jetting, how you are injecting the material. So based on the process only, the process is different, but the concept of the additive manufacturing is basically common. The droplets, the droplets may be distributed continuously or individually using the drop on demand method, similar to the inkjet printer. That is, which area the droplet should be injected to the field. The particular based on the CAD modeling data, the particular place only the droplet should be spreaded. The material jetting can be done with the various materials, including the polymers and waxes. These are the typical examples for the material jet based prepared components. The material is one of the most accurate 3D printing technology because of the printers spray the resin in the tiny droplets that is a less than or equal to 70 micrometer. Only it splits the three-dimensional object with the multiple layers. The main components are printer heads, ultraviolet light sources, and build platform and material containers. The print heads and light sources are suspended along the same x-axis, carrying the strip specs and both across the print bed depositing the curing material simultaneously. The tonsils of sprayed droplets are tiny and cured instantly through the no oozing or cooling. This method is capable for high precision build and smooth surfaces. This is a typical example of how this droplet should be spread out over the build platforms. And next one is the binder jetting process. The binder and the powder-based binder is the powder-based material process. The powder-based is material supplied on the build platform with the roller. Initially, the powder is spread over to the platform. Once the layer is finished, the roller should be spread out the powder on the above the layer. Once the binder droplet should be filled on the which record shape we record from the bed. The binder adheres the layer together usually on the liquid form. Following the product in the layer form, this is repeated to create the more layer until the product is finished. The materials, commonly used materials are polymers, ceramics, and metals. The speediest additive manufacturing method allows for customization. The specific quality, they change the binder powder ratio to create the product that has the color variation. The drawbacks of binder jetting process increase in post processing time, and it may not be best as for creating the structural parts because the it is required the post-processing methodology used in the industrial application, dental and medical devices, and aerospace components, and podcasting and luxury applications. So, what are the basic characteristics of energetic process? Generally, they are using the metals and the ceramics and dimensional accuracies plus or minus of 2%. And typical build size are 200 to 400 into 250 into 50. For industrial application, 2200 into 1200 mm. Common layer thickness of 35 to 50 micrometer, and supports are not required for this process. Our next process is the sheet lamination process. It is a process of building the 3D object by stacking and laminating the thin sheet of the material. The lamination method can be bonding, ultrasonic welding, or bracing, while the final shape is achieved either by the laser cutting or CNC machining process. There are two variations of the sheet lamination. One is the ultrasonic additive manufacturing and laminated object manufacturing. The difference between the two is found to the material used under the bonding process. The ultrasonic additive manufacturing is the metal that is bound together with the ultrasonic welding, and laminated object manufacturing is bound together by using of adhesive manufacturing. From the bound process, sheet metal is cut to the shape first, and they bonded to the base of previous layer to create the three-dimensional geometry. Bond for the form process. In this process, the name suggests the sheet metal layers are bonded together before cutting them into the desired shape. So, sheet lamination process category in the seven different process. One is the LAM, and SLCOM, PSL, CAM and SDL and CBAM and that is laminated object manufacturing, selected lamination, composite object manufacturing, plastic sheet lamination, computer-aided manufacturing of laminated engineering materials, selective deposition lamination, composite-based additive manufacturing, ultrasonic additive manufacturing. The thin sheet of metal is fit from the roller or placed on the build platform. Depending on the type of sheet lamination, the next layer may or may not be bonded to the previous sheet. The STL and UM bond the layer together and then cut to the 3D shape at the end of the end, while the CAM layer cut the layer into the shape and then bonds the layer together. This process continues until the completes all the layer to achieve the full height. Then the print plug is removed and the unwanted outer edges are removed by reveal the printed 3D object. In the sheet lamination, the layer thickness is same as the thickness of the thin sheets of the material. The layer thickness also depends upon the machine and process to be used for the manufacturing process. This is the example for laminate object manufacturing process. It should that is a material sub. This is the material supply roller. It is supplying the material to the build platform. So this optical laser should be passed through the through the X-ray plotter. Whichever object we locate based on the 3D modeling, the laser should be passed through the process. The particular component should be only melted and cured on the build bed. After that, the metal should be excess metal should be recovered by the material recover. One second, the material should be passed over the build platform. The same laser should be passed over the particular area. The final component should be produced by layer process. And next one is the polymerization. This is a support structure will often need to be added. The resins are cured by using of photopolymerization process or ultraviolet light source, where the light is direct across the surface of the resin, where the use of motor controlled mirrors, where the resin comes into contact with the light, it gives our hardness. Some of the wet polymerization techniques are stereolithography, direct light processing, and mask stereolithography method. This is a step-by-step procedure for wet polymerization. The build platform is lowered from the top of the resin, what downwards by the layer thickness. The UV layer light gives the resin by layer. The platform continues to move the downwards, and additional layers are built up on the top of the previous. Some machines are used the blade which moves between the layers in order to provide the smooth resin base to build the next layer on. After completion, the wet is drained of resin and object is removed from the build platform. So you can see the resin is completely filled on the resin is completely filled on the platform. This is the curing device. You can use the laser light source or ultraviolet light source or digital light source. The digital light source should be passed over through the resin surface. Whatever object we require based on what we created in the 3D modeling, that input should be given to the machine. From the machine that passed through the ultraviolet light source, this depends upon the object we require. It should be passed over the layer by layer. Once the initially the platform should be positioned on the upper of the surface. Once one layer is completed, then it will be go for a download. Then next layer should be processed. It will be processed by layer techniques. Finally, we can get the final object. The entire resin should be drained from the bed area. Finally, we can get the final object from the device. And next one is a powder-based system. The layer of powder is applied to the platform. Thermal energy source like an electron beam or laser fuses the powder before the second layer is applied with the roller or blade. This layer process is then repeated. So some of the powder-based system processes are selective laser melting, selective laser sintering, electron beam melting, direct metal laser sintering. Here in the first process, we are using laser source for melting the powder. In the second source, we are using laser for sintering the powder. And third process, we are using electron beam for melting the powder. And fourth one is directly metal is sintering in the bed. So first one is the powder bed fusion process. it is either laser or electron beam to melt or fuse the metal powder together. We can see here, this is the powder is completely filled on the powder is filled on the platform. Here, this is the fabricated area. This is the laser source. The laser source comes to the scanner system, and it should be laser should be passed over through the powder bed area. Whatever object we can record based on the dimensional, the laser should be spread on the powder bed area. So, for example, here in the bottom of the fabricated portion, we can record the continuously 20 to 30 mm. Laser after 50 to 60 mm gap, later we record the 20 to 30 mm melting area. So, based on that area only, the laser power source should be directed. The remaining area laser power should be passed through the powder. Where the laser power should be passed, that particular area of metal should be melted and should be cured on the powder bed. Once the layers is completed, the powder delivery pressure should be spreaded the power above the cured layer area. The electron beam melting methods require the vacuum, but can be used with metals and alloys in the creation of functional parts. All powder bed process are involved in the spreading of the powder material over the previous layers. There are different mechanisms to enable this, including the roller or blades. A layer is typically 0.1 mm thick of material spread over the built platform. The laser fuses the first layer or first cross section of the model. The new layer of the powder is spread across the previous layer using the using the layers. This process is repeated until the entire model is created. Thus, the unfused powder is, remains in the position, but is removed during the post processing. The major advantages of powder-based resources are it gives a very high accuracy, excellent surface finish, and integrative geometries. For direct energy deposition, generally we are using the metal powders or wires are the most common material used, but ceramics and polymer powders also make, may be used. It can achieve the high degree of accuracy due to the due to the ability of repair and control grain structures in direct energy deposition process. The finish varies based on the material used. In case of metal, powder will provide the better finish than wire. So DED creates the 3D object by melting and depositing either powder-based or wire-based materials from a focused thermal energy source, including the laser or the electron beam or plasma or the metal, ceramic, and polymer parts are mainly used for metal parts and in more hybrid manufacturing, where the subtract the bed is movable to create the complex shape. The DD also referred as the laser metal deposition, 3D laser cladding, or direct light fabrication because of the different energy sources used for the final sources. The direct The challenges in the direct energy deposits are high material cost, slow production rate, and the poor surface finish and post-processing requirement, limited mechanical properties, and high machine reliabilities. And how does the direct energy deposition works? You can see this diagram, you can easily understand. This is the deposition layer, this is the multiple. This is the laser beam, the metal powder or metal finish should be comes through this, through the arm. The laser beam should be melted the metal and it should be deposited on the bed area. And typically, the direct energy deposition metal they are using manufacturing with the metal parts. This process can be also used for the polymers and the ceramics. Almost any weldable metal can be additively manufactured by using of direct energy deposition process. Especially this process is used for fabricating the components for aircraft parts and the submerged parts, including the most widely used metals are aluminum, inconel, niobium, stainless steel, and tantalum, titanium, and titanium alloys, and tungsten materials. So these are the challenges with the 3D printings: the high cost of materials, unreliability of missions, rejection rates, and challenges of scaling of technologies, speed, environmental concerns, surface niche, and mechanical properties and post processing. Especially for the challenges in the scaling up is basically we are manufacturing the component with the prototype model, but we are going for the real-time application, real-time increasing dimension that is completely difficult, and initial cost is more. And next one is the application of artificial intelligence in the 3D printing. Over the past decade, the additive manufacturing technology has made a significant strides and found diverse application across the sectors like in the healthcare, aerospace, and construction, and contributing to its growth in the multiple engineering sectors. Notably, artificial intelligence has to play the pivot role in analyzing and supporting the integrate physical phenomena associated with the additive manufacturing. Generally, it should be contributed to the four different categories. One is first thing is AI streamlines design process by considering the additive manufacturing, that is selecting of specific parameters and promoting the innovations. And second thing is it facilitates the material development, creating the customized material for the additive manufacturing. And third one is AI optimize the additive process through the real-time control, improving the process selection and execution. And fourth one is AI ensures the quality through the predictive models and the real-time monitoring. So in the machine learning helps identify the suitable materials, predicting the mechanical properties, and developing the new material composition much faster than the conventional experimental approach. For the design for specific design for additive manufacturing is AI automatically generates the lightweight and optimized design for reducing the manufacturing cost. For process management wise, the AI continuously monitoring the printing parameters and automatically adjust the temperature and the speed and the layer thickness for improving the product quality. The first one is AAS is design for additive manufacturing. The design for additive manufacturing is the design technique proposed to apply the additive manufacturing technology toward the reducing the production cost and production time while ensuring the product performance and quality. The product manufactured through the design for additive having the complex shapes that are difficult to manufacture in conventional machining and mold-based machining, and geometry and functional combination must be considered. Therefore, the active research in the use of artificial intelligence in effective use of design for additive manufacturing is ongoing. Yes, please. It is optimize the products for additive manufacturing, reduce the production cost and manufacturing time, ensure the high product quality and performance. AI enhance the design for additive manufacturing by optimizing the design parameters and designs, minimizing the failures and improving the material utilization. Makes additive manufacturing for both experts and non-experts. So major artificial applications in the additive manufacturing are yearly geometry error prediction. That is a defects and corrects the design error before the printing, and cost build time estimation, predict the manufacturing cost and printing time based on the previous data and generative design. Creates the optimized and lightweight and high performance designs. Design rules generation. It generates the design rules based on also the manufacturability by using of AI based recommendation. So, what are the AI techniques generally used for the design for additive manufacturing? Are conventional neural networks, random forest methodology, or artificial neural networks, genetic algorithm, or the deep learning process may be used for uh, creating the design for manufacturing, additive manufacturing. The benefits for application of AI in DFM are improve the print accuracy, reduce the manufacturing defects, lower production cost, faster design optimization, and better material efficiency. So AI is significantly improves the design for additive manufacturing by optimizing the design, cost, quality, and performance. It enables the efficient and intelligent additive manufacturing for real-time applications. And the next one is AI assisted material development. So materials are the core element determining the structural characteristics of additive manufacturing output, and accordingly, the focus of most of the research is development of new materials for the additive manufacturing. For example, previously we can use the customized material PLA, PEEK, and ABS, and some of the materials, commercially available materials only we are using for 3D printing. But nowadays we are focusing for the bio-based material. That is, you are using of natural filler materials or some of the bio-based materials for adding into the commercially available biomaterials for enhance the mechanical properties and the structural properties also. In particular, the use of artificial intelligence in the development of materials for additive materials has the following advantages. One is the high predictive accuracy for mechanical properties is exhibited despite the low training data density and small batch sizes and the small training group count. The hidden relation between the different printing parameters are effectively identified, and the guidance as to chemical synthesis pathways is provided. Low cost and time requirements compared to the design through the direct experimentation and fabrication allowed for accelerated material design. The, the example for AI, how assists to the material development for the additive manufacturing. Suppose we are selecting combining of new variety of alloy material or composite material. So based on the existing material properties, the artificial intelligence gives suggests the which fabrication parameters suitable for the materials. For example, we are making the eggshell based PLA material. What is the temperature for eggshell material? What is the basic temperature for PLA material? So based on the combination, the AI should be suggest the which temperature range is suitable for printing this material. This is the application of AI as the material development for additive manufacturing. So AI in the material development. Artificial intelligence enables the redesign for conventional materials for additive manufacturing by improving the material selection development and property prediction. For example, we are going for the new component based. We are going to select the material. So AI will give the based on the requirement of the component, it will suggest the material, which material should be easily bonded with the existing material, which will based on the cost, based on the aesthetics, based on the speed, based on the process parameters, it will give some suggestions based on the final output of the product. AI uses the machine learning and the multiple criteria MCDM techniques to identify the suitable material with high accuracy for the additive manufacturing process. AI optimizes the lattice structure and meta materials using the advanced algorithm to achieve the superior mechanical properties and lightweight designs. And AI enhances the existing material by modifying their microstructure and composition, leading to stronger and more efficient for the additive manufacturing process. And that one is the AI assisted process for uh, management for the additive manufacturing. The output quality is directly affected by the process variables in the additive manufacturing because the print bed temperature is not suitable. The entire product should be waste. The nozzle temperature is not adapted for the material. Entire output is waste. Yeah, the environment is not suitable for the manufacturing. Entire product is waste. So output quality is directly affected by the process variables in the additive manufacturing. In the early stages of additive manufacturing, statistical approaches such as the analysis of variances through the design of experiments method were applied to determine the correlation between the process variables and the output code in the additive manufacturing. So basically, whatever we are going to the manufacturing by using additive manufacturing, definitely we have some input parameters as well as the output parameters. Based on the output parameters, based on the output strength, we are identifying the input parameters based on the output properties only. But generally, it was correlated by using of ANOVA methodology or design of experiment methodology or some of the techniques previously used. But nowadays we are utilizing the artificial intelligence techniques for connecting this input parameters with the output parameters. However, the methodologies for applying the improved cognitive learning and interface the capability of AI are being developed, and case of relation of the same in additive manufacturing process management are increasing. AI is being used in the process management to optimize the process variables or modifying process variables in the real time towards improving the output quality. In this section, the use of artificial intelligence for process management is explained and examples are introduced. And fourth one is the AI assisted quality prediction for additive manufacturing. The maintaining the standardized output quality of additive manufacturing outputs is the key to increase the utilization of additive manufacturing techniques. However, it is difficult to maintain the standardized output quality for additive AM techniques, wherein individual products are manufactured independently in individual AM equipments. In particular, as the output quality of AM outputs is impacted by the various factors such as the process variables setting mentioned in the previous section. That is, what are the input parameters, process environment, position inside the equipment, process method, and it is highly difficult to predict the output quality for the given process condition because each and every parameters plays a vital role for the output quality of the component. Even though any one of the input parameters will not suitable for the printing process, it should be completely affect the quality of output product. Okay, so since the verifying the output quality through the repeated fabrication requires the much time and the cost. Many studies have been conducted. Many studies are already conducted to predict the output quality by simulating the physical phenomena that manifest in the process. Recently, the research has been conducted to use of AI techniques to predict the output quality based on the various signals that occurs in the process. So these are the advancement of artificial intelligence, how it's in place on the additive manufacturing process. In this slide, I show some of the additive manufacturing process. What are the input? What are the output? What are the machine learning techniques they are used for calculating the insight to defect detection through the machine learning methodology in the additive manufacturing. First one is the material extrusion process. Their input process are build plate process temperature, build plate process temperature, extruder temperature, and material temperature and vibration. So defects for the material extrusion is surface roughness. So they are using the random forest method, support vector regression method, ridge regression method, least absolute shrinkage, and selective operator method were used for calculate the surface defects in the material extruder process. And the same material extrusion, monitoring image 3D scanner data, the outputs are geometrical defect. They are using kernel neural network and SUM bagging and random forest and GB methodology, machine learning methodology used for detecting the error. And next one is the powder based diffusion process. The input, what are the inputs they are considered for monitoring image, thermal monitoring image, and acquisition image. What are the output they are considering is manufacturing defects, reporter hopping, sticking, debris, super elevation, pot failure, incomplete spreading, delamination, starters, porosity, result quality, and porosity. So they are using CNN, unsupervised learning, and LR, assumed logistic regression, random forest, and Adaboost technology, spectral convolutional neural network based machine learning are used for detection of errors in the powder bed fusion process. For direct energy deposition, thermal monitoring image system parameters, thermal monitoring image by using of acoustic emulation. The output results are porosity, result distortion, and cracks, porosity cracks, and equal pores. They are using different AI techniques for identifying the in situ defect detection by using of machine learning. So nowadays the machine learning things, artificial intelligence and machine learning techniques are widely used for finding out the defects in the additive manufacturing by using of based on the images as well as the readings also. So in this session, finally, we are going to discuss about one of the artificial intelligence techniques named as the fuzzy logic algorithm. So already in the market, they are having a number of artificial intelligence tools are available as the AN and artificial neural network, neurofuzzy system, physiologic system, MCDM, multi-criteria decision making, and a number of machine learning, random forest, black sea, a number of machine learning algorithms are available in the websites. So artificial neural networks and physiologic systems are two types of modeling and prediction method, have gained the popularity over the past 2 decades and get used for many researchers in the wide range of engineering application. So first of all, what is physiology? Physiology is working based on the mathematical theory only. It is based on the imprecision, especially the way of people making decision on imprecise or non-numerical information. The physiology mimics the way a human makes the decision by using of linguistic reasoning. It is based on the mathematical theory combining the multi-valued logic, probability theory, and artificial intelligence method, and can be used to tackle the complex problem. It is based on the first set theory, and linguistic statements are expressed mathematically, which correspond to the analysis of human experts. This is the structure of physiological system, how it works. Basically, we are creating the inputs and output variables in the fuzzy interface system. That is, I will explain the case study later. And the next step is based on the input and output variable, the fuzzy it will create the membership function in the MFF editor. Later, then based on the if then else condition, we are creating the rules with the specification variables. Later, then fuzzy appropriate reasoning with the Mamtani method, and finally despecification in the centroid method. Finally, we will get the prediction values based on the expected results. So you can open the MATLAB. You can start the fuzzy logic. Go to the toolbox and more fuzzy logic FIS editor. So once you are clicking the FIS editor, you will get the basic fuzzy logic screen. So it's having one input and one output. One is the hidden layer. So based on our input, you can increase the n number of input layers. Based on the output, you can increase the n number of output. For example, in this case study, I am taking the two inputs and three outputs. The input named as the temperature, and another one input is the direction. For output is the tensile strength, yield strength, and elongations. In first logic, we will have basically having the two methodology. One is the Sajino methodology, another one is the Mamtani method. Mamtani method is universally used for first logic, and the Sajino method is commonly used for neurofuzzy modeling method. The fuzzy interference is the method that interprets the value in the input vector, and based on the user-defined rules, assign the values of the output vector. Using the graphical user interface editor and views of the fuzzy logic toolbox, we can build the rule set, define the membership function, and analyze the behavior of fuzzy interface system. Here I am taking the 10 inputs, temperature and direction. So temperature is 3 levels, 4 levels, 650, 800, 1000, 1100, and 1200. And directions are horizontal and vertical, only two levels. And temperature is 5 levels, 650, 800, 1000, 1100, and 2000. So here I am selecting the two input variables. One is the temperature, another one is the direction. So based on the input values, I will make the fuzzy condition for the input values. 650 is taken as the low, and 850 is taken as the low medium, and 1000 degrees centigrade is the medium, 1100 is taken as the high medium, and 1200 is taken as the high. The horizontal direction is taken as the low, and the vertical direction is the high. These rules conditions are completely created by our own idea. Previously, I selected as the three output responses. One is named as the tensile strength, yield strength, and elongation. So based on the mechanical test, I collected the data of tensile strength values of 612, 516, 593, 581, 531, 529, 499, 481, 516, and 493. Yield strength similarly for the yield strength, similarly for the elongation. Based on the result, we are creating the conditions. Which one is the low value? Which one is the high value? You can see out of this 10 readings, 481 is the very low, and 612 is the highest value. So in between the low to high, I classified the results as the low, medium, low, medium, medium, high, medium, and high. Similarly for the yield strength also. Similarly for the elongation also. So based on the results, you can select any one of the output parameter, tensile strength or yield strength or elongation. You can categorize the values. So 0 to 240 you can see here. Yield strength low is up to 216. Low medium is 216 to 280. Medium is 280 to 320. High is more than 320. So based on that, we are creating the membership function in the fuzzy membership plotters. After that, we are creating the fuzzy set rules based on the, there is the first step, design the rules based on the fuzzification variables. We are creating the rules. Already we are formed the rules here itself. Later that it should be tabulated in the tabular column manner. So 650 is low, 650 is low, 800 is low medium, 800 is the low medium, 1000 is medium, 1100 is high medium, and 2200 is the high. So based on the first condition, the temperature 650 is low and direction is high, the tensile strength is high and yield strength is high and elongation is high. The same rule should be developed in the fuzzy rules editor. Okay, it is a complete data set developed in the input values as well as the output values. Both the input and output values are tabulated in the single tabular column. So what is the first experiment? 650 degrees centigrade, that is the low condition, and direction is horizontal, that is also low condition. What output we got from the experiment? 612, that is high, and yield strength is high and elongation is low. Based on the values, we are creating the rules in the fuzzy rules editor. Similarly, for the 10 experiments, we are creating the rules editor. Finally, we are going for the rules viewer. In between that, we are expecting, we want to predict any one of the results. You can get the result from the fuzzy rule editor. Here you can see what are the temperature we have in the what are the input values? We have the temperature 650, 800, 1000, 1100, and 2000. For example, we want to know the temperature of some 750 degrees centigrade. We want to the direction of horizontal or vertical. We will get the tensile strength from the fuzzy rule viewer by changing of the values in the input condition. But you can see this slide, you can easily understand. I need the temperature of 925 degrees centigrade and the direction is horizontal. So similarly, you will get the tensile strength value of 560, yield strength of 300, and the elongation value of 42.5. Okay, so the fuzzy rule it shows the detailed view of figure of fuzzy interface system to diagnose the specific rules or study the effect the change of the input values with respect to the prediction. Similarly, we can get the surfaces from the fuzzy surface viewer with correlation of different input and output parameters. Hello.
Hello, sir.
Sir.
Sir. Nothing, sir. Your presentation is over, sir.
Over, sir.
Yes, okay. Participants, so do you have any queries? Please let us know. Dear participants, the session is completed. So if you have any doubts from the session, just let us know. Or else just post your question in the chat box. We'll wait for a while, sir. So if there are any questions, we try to answer it. So after that, we will conclude the session, sir.
Thank you, sir.
So, dear participants, so do you have any doubts? Just post it in the chat box, or else you just unmute yourself and let us know. Sir, sir, there is a questions in the chat box.
Ah, can use the mechanical photos. No, sir. Mutumar, sir. Sir asked that at the same time we can use the ceramic powder or metallic paint, metal based.
Dear participants, so do you have any questions or doubts? You just please post it in the chat box, or directly just unmute yourself and let us know. Sir, I think there is no questions from the audience. So shall we conclude the session, sir?
Ah, okay, sir.
Yes, sir. Thank you so much for interesting and insightful session. So on behalf of Department of Mechanical Engineering, so I thank Dr. N.S. Balaji, Assistant Professor, Department of Mechanical Engineering, SRM University, for being a part of this faculty development program. Thank you so much for being with us and sharing your knowledge with us, sir. Thank you so much.
Thank you, sir. Thank you, sir. Once again, I thank to the coordinator of this event, Aravind Raj sir, and another one, Aravind Raj sir, another one person.
Sadish T.
Ah, Satish sir. Once again, I thank you, sir, and I thank to the management of Weltec Group, sir. Thank you, sir. Thank you for the opportunity, sir.
Thank you, sir. Thank you so much.
Ah, thank you.
Dear participants, so the day 5 session 10 is over. So just we will post feedback form shortly. You kindly fill up the leave your feedback using link. Thank you so much. You can leave the session now. Thank you.